Hello dear students, in today's class we will discuss the working of a phase meter. So you might know about the term phase. This is a term that we use in the case of waves. Here we consider electric signals in the form of waves, such as an AC current or something like that. So when we say about phase difference, we mean what is the relation between the phase of two different waves. So here you can see two waves that are in phase. When these waves are in phase, they grow together and the negative half cycles of them also coincide. Their variation with respect to time goes hand in hand. So this is an example of an in-phase wave, a single wave followed by the second wave, which are following the same pattern. So this happens when the frequency are same. So here you can see an out of phase situation between two waves. They lag between each other, and this is an example of completely out of phase waves. The positive half cycle and the negative half cycle of the waves coincide with each other. So during the positive half cycle of the first wave, we have the negative half cycle of the second wave, and so on. So in a phase meter, we will try to measure the phase difference between two different waves, two different electric waves. And accurately, we will not be measuring the exact phase difference. We will be checking whether the waves are in phase or whether the waves are out of phase. In this device that we are going to see, it could be detected whether the waves are in phase or whether they are out of phase using this mechanism. So let us try to understand this internal circuit of phase meter. So here we have two different coils here where we could feed in the two different signals that we have. So the signal 1 could be fed in here through this primary coil, and we call the voltage of the signal 1 as VR. So this is sinusoidally varying signal voltage. And we have the second wave here, and we call the voltage of the second wave as PS, and it is also a sinusoidally varying voltage. We want to compare the in-phase or out-of-phase situation of these two waves. So these two are the places where we feed in the voltages. And as you can see, this voltage is getting transferred to the secondary of the coil through induction. And the secondary of the coil will develop a voltage corresponding to this input voltage. So in the case of the first voltage that is fed in here, VR, here we have three terminals. This is the ground terminal or the center tap. We can assume the potential at this point to be 0. So if we feed in a VR voltage here, we can assume that in the upper half of this secondary coil, a plus VR voltage will be developed during the positive half cycle, and a minus VR voltage will be developed in the lower half of this coil during the positive half cycle. So in the positive half cycle of the signal 1, in the secondary coil, we have actually 2 VR voltage, just like the center tap transformers that you see in your labs. Here the voltage corresponding to the central part is often taken as 0, and the other two terminals at the extreme points, one develops a VR voltage and the other one develops a minus VR voltage, all during the positive half cycle of the signal 1. Positive half cycle of this signal here. And at the same time, we are feeding in the second voltage here, and we will look into what happens to different components inside. And straight away, if I tell you what is the difference between in-phase situation and out-of-phase situation, that is actually detected by this galvanometer present here. This galvanometer will indicate a right deflection if the signals are in phase. The signal VR and the signal VS are in phase. And if they are out of phase, this galvanometer will indicate a left deflection. So as I have already stated, we can only know whether the signals are in phase or out of phase using this device. And the deflection on the galvanometer towards the right or towards the left in fact tells us whether the signals are in phase or whether they are out of phase. So let us try to understand the mechanism of this right deflection and left deflection that happens for in phase and out of phase waves. First, let us try the case when the signals VR and VS are in phase. So they are in phase means during the positive half cycle of this VR, the VS is also having its positive half cycle. That means we have a plus here and a minus here. So this corresponds to the positive half cycle of first wave, and this is the positive half cycle of the second wave. So if I plot the negative half cycle, it will look like this. In phase waves actually means these positive half cycle and negative half cycle happen synchronously. Now let us consider this positive half cycles. Let us consider a case when we are feeding in phase signal VR and VS. And let us understand what will happen to the circuit. So to understand this in-phase situation, we should understand what will happen if Vs is equal to 0. Suppose I am feeding in no voltage at this point. All that I feed in is this VR signal here. So as you know, when we feed in the positive half cycle, here we will have plus VR, here we will have 0, and this is negative VR. So as you can see, here the diode 1 has a forward bias condition under this case. The positive is connected to the diode positive and the corresponding negative or the ground is connected to the negative of the diode 1. That means the diode 1 is forward biased in the positive half cycle, and as a result we will have a current conduction through the upper half of the circuit in this direction, from the positive to the negative to the ground. In this direction you will have a current flow. Whereas in the case of the lower half, you can see this is ground, this is negative voltage. So the negative is connected to the positive of the diode and the ground is connected to, or comparatively the positive is connected to the negative. That means the diode 2 is reverse biased and hence no current will flow through this lower half of the circuit. So during the positive half cycle, if we have no Vs here, during the positive half cycle we have a current in this direction through R1 and the galvanometer here will show a right deflection during the positive half cycle. So note down, when a current is flowing through R1 in this direction, the galvanometer will indicate a right deflection corresponding to a voltage. That is because the galvanometer is connected across both R1 and R2, and a positive voltage developed here actually indicates a right deflection on the galvanometer, indicating a positive voltage. Now let us consider the case of the negative half cycle of this same VR signal. Then we have negative voltage here and positive voltage here, since this is the negative half cycle, and let us try to understand the polarity in different loops in the circuit. So a negative voltage here implies we have a negative voltage developed here. This is ground, which is 0, and the positive voltage will be here. This voltage is 0 as we have already stated. So in this situation, the diode 2 is actually forward biased because positive is connected to positive and the negative is connected to the negative. So this is forward biased, and similarly you can see the diode 1 will be reverse biased. Negative is connected to positive. So the diode 2 will conduct during this half and the current conduction will be in this direction through the diode. So this is the direction of current conduction through R2. So during the negative half cycle, the galvanometer will indicate a left deflection. So during the positive half cycle, we had current conduction in this direction along R1 downwards, and the galvanometer indicated a right deflection, and during the negative half cycle, diode 2 conducts and R2 has a voltage which allows a current to be flown in this direction, upward direction, and the galvanometer will show a left deflection. Now we know any signal consists of a large number of positive and negative half cycle, which is repeated many times during 1 second. For example, in the case of an AC signal, we have 50 such cycles in 1 second, which is the frequency of AC, 50 per second. So that means that this galvanometer will execute right deflection and left deflection alternatively almost 50 times in a second, which means that the galvanometer will choose to stay at the middle point, indicating a balance between both positive half cycles and negative half cycles. So if something is oscillating at very high rate to left and right, it will not be able to execute both these motions, and apparently it will stay fixed at this mean point. So what you will observe on this galvanometer is a null deflection, because due to this balancing of positive half cycles and negative half cycles, which are repeated many times during 1 cycle. So this is the situation when Vs is equal to 0. We have null deflection on the galvanometer. Now let us turn our attention to this case when we have two signals here. Vs is not 0 and we are feeding in an in-phase voltage signal here, Vs. So that means that when we apply the positive half cycles of the Vr here, we will also have the positive half cycles of the Vs2 corresponding to an in-phase situation. So as we know, during the positive half cycle, the voltage across this secondary is positive, 0 and negative Vr. Here we have positive and negative of Vs. This is Vr. So as a result, as you can see, in the upper half of the circuit, we have the voltages that is getting added. You can see a positive is connected to a negative and again a positive. So this corresponds to a situation when we add together certain cells like this. A 2-volt cell, its negative is connected to a positive of 3-volt cell. So this will correspond to a 5-volt equivalent cell. So same situation is obtained here. The Vs signal and the positive Vr signal, they are in phase here in the upper cycle, and we have a voltage of Vs plus Vr in the upper half of the circuit. The voltage developed across R1 is Vs plus Vr, and this voltage actually forward biases the D1, the diode 1. So we will have a current flow through the R1, and we will see that is equivalent to, that is actually due to this voltage Vs plus Vr that is developed in the upper half. Now let us look into the lower part of the circuit. There we have the Vs voltage, but the minus Vr voltage is developed here, and this Vs and Vr are actually not aligned in an additive manner. So you can see the positive of this Vr voltage is connected to the positive of the Vs cell. Situation is like this. This is the Vr and this is Vs. So the effective voltage is actually the difference between them, Vs minus Vr or Vr minus Vs, whichever is greater. So this is minus Vr, negative is here and the negative is here. The positives are connected together, and as a result, the voltage along the bottom half of the circuit is Vs minus Vr if Vs is greater than Vr. While as you are seeing, the upper half develops a voltage of Vs plus Vr. All this during the positive half cycle itself. So as you can see, we have a higher voltage at the upper half, indicating that a higher current will be flowing through R1, and we have only a small current in this lower half, and only if fortunately Vs is greater than Vr. Otherwise, if Vs is lesser than Vr, D2 will be reverse biased in fact, and there will be no current at all. So if Vs is greater than Vr, there will be a small voltage in the lower half, which is Vs minus Vr, and we will have a very small current in R2. So balancing these two, the galvanometer will actually show an indication, a deflection towards the right, because the voltage in the upper half, this voltage Vs plus Vr dot voltage dominates. This is a feeble voltage, small voltage, and that is actually negligible. So you can assume that there is no voltage in the lower half, and the upper half has a higher voltage leading to a current and leading to right deflection of the galvanometer. This is what happens in the positive half cycle. And during the negative half cycle, again these are in phase situation, in phase signals. We are considering the negative half cycle. So during the negative half cycle, this is the situation, and here negative and positive. So here we have a negative Vr, this is ground 0, and here we have positive Vr. So you can see that during the negative half cycle, the upper half has an adding effect for the voltages. Here a negative, this is its equivalent positive, again it's negative, again another positive. That means we will have Vs plus Vr voltage in the upper half, but that voltage is actually reverse biasing D1, because the positive is connected to the diode 1 and the negative is connected to diode, the positive of the diode 1. So this is reverse biased even when the voltage is Vs plus Vr. So let us neglect the case of upper half during the negative half cycle. And lower half. Again in the lower half, we have negative and positive voltage. This is 0 and positive voltage. So this is Vr and this is Vs, but they will not add up because the negatives are connected together. What you will have is Vs minus Vr voltage again in the lower half. So upper half is not at all conducting, and the lower half has a low current of due to the voltage Vs minus Vr. So during the negative half cycle, the deflector, the DC meter, the galvanometer will show a leftward deflection corresponding to the voltage developed across R2. So let us re-emphasize what we have learned. During the positive half cycle, for in-phase signal, during the positive half cycle, the voltage in the upper half is Vs plus Vr, and the voltage in the lower half is Vs minus Vr. And as a result, the galvanometer will show a huge right indication, right deflection. Huge right deflection. Why huge? Because the deflection is due to this voltage Vs plus Vr. Now during the negative half cycle, all voltages are reversed in phase, but as we have seen, the voltage developed in the upper half is minus of Vs plus Vr, or a voltage that is reverse biasing diode 1, and in the lower half we again have Vs minus Vr or Vr minus Vs voltage. So you can see that actually leads to a lower deflection of DC meter towards the left. So a low left deflection is what happens during the negative half cycle. So when this happens a lot of time during 1 second, during positive half cycle, the galvanometer will deflect towards the right in a large amount, by a large amount, and during the negative half cycle, the galvanometer will deflect towards the left by a small amount. And balancing these two, when this is repeated for 50 number of times or n number of times, on an average, this galvanometer will show a right deflection, because the right deflection is more and the left deflection is small. This is due to the special case of in-phase signals, this development of voltages and their addition rules, they actually contribute to this effect. So this is how during the in-phase waves, during their positive half cycles and negative half cycles, the galvanometer deflects differently and overall leading to a right deflection in the case of in-phase signals. Now let us try to understand the case of out-of-phase signals. So if the signals are out of phase, that means positive, negative, and this Vs is out of phase. During the positive half cycle, we have the equivalent negative half cycle of Vs, and here this is correspond to the negative half cycle. So this is the out of phase situation. So you can see that the exact opposite condition that we have mentioned here will happen here. During the positive half cycle, Vs plus Vr voltage will be developed here and Vs minus Vr will be developed here in the upper half. And during the negative half cycle, a minus of Vs plus Vr will be developed here, leading to no current during the no current along this lower half, and again a Vs minus Vr in the upper half, leading to a small current. So the galvanometer will show a large deflection towards the left side during the negative halves, during the positive halves, and a small deflection towards the right side during the negative halves. So as a result, overall this galvanometer will show a left side indication because we have a large amount of left deflection due to this Vs plus Vr voltage during the positive half cycle of Vr. So draw this circuit diagram and try it out for yourself how the circuit will behave in the case of an out of phase signals Vr and Vs. So you can easily see how this left side indication or leftward deflection comes about. So understand about this in-phase situation and you can automatically extrapolate the idea to get how this circuit will behave for out-of-phase situation. So I hope this concept is clear for you. The working of phase meter is clear for you. Thank you.